Welcome to class. Today we're going to be looking at rules of logarithms. Rules of logarithms. As a start, it is important we note that if p is equals to b raised to power x, you can see that expression. Alright, so if you have a number such that the number p is equals to b raised to power x, it is the same thing as saying that log p in base b is equals to x. So as a start, we are going to be building foundation on this rule. We're going to be building on this foundation rather. And this expression is vice versa. If log p in base b is equals to x, it also means that writing this expression without the logarithm is the same as saying that p is equals to, why I put this phrase is to demonstrate that b will now carry x as a power. X will become the exponent and b will become the base. Alright, so this is equals to b raised to power x. Alright, so in this kind of expression, b is the base, x is the exponent. So the power or the exponent is the answer to the logarithm of p in the base p, in the base b rather. So this is vice versa. Now that we have established that fact, it is also important that we also look at another number q. Alright, so if q is equals to b raised to power y, it also means that log q in base b is equals to y. Before we proceed, we note the fact that if p times q is something, that pq is something as p times q, remember p was b raised to power x, so p times q means b raised to power x times q is b raised to power x. From our rules of indices, if you multiply indices of the same base, what you do is that it is simply saying that this is the same thing as b raised to power x plus y. And if we do the same thing here, the same thing as saying that b raised to the power x minus y. Alright, because they are the same base. Now, remember what we have established here. So, we can go ahead to say that log pq in base b is the same thing as x plus y. Yes. Or we can say this, that pq is equals to, I don't want to log, remember, equals to b raised to the power of x plus y. I believe what we are doing here is very similar to what we are seeing here. Alright. From the second statement, if p over q is equals to b raised to power x minus y, alright, we can interchange this and also say that log P all over Q in base B, let's put this bracket here, just the same way we put this bracket here, is equals to x minus y. We can also say that if this base carries this up, that P all over Q is the same thing as B raised to power x minus y. If you look at this critically, we are doing the same thing from the front to the back and from the back to the front, vice versa. So watching this critically will give you a good understanding of these laws. All right. So I can call this the law of multiplication. All right. The law of multiplication. I can call this the law of division. Yes. That multiplication, yeah, will lead us here, and division will lead us there. But this will make just a bit more sense when we look at what we're going to look at right now. Stay tuned as we look at the next step. Formally, at the first row, log PQ in base B is given as log P in base B plus log Q in base B. Recall the previous step that log P in base B was derived as x and log Q in base B was derived as y. So this is equals to x plus y. Rule 2 in summary is that log P all over Q equals to x minus y. Remember, when logarithms of the same base, you have a numerator and denominator, you can express it as log P in base B minus log Q in base B. And that is the same thing as x minus y. So the rule is simple. When it is multiplication, you add, and when it is division, you subtract. All right. We move to the third rule. Rule 3. So if we have log P raised to power n in base B, log P raised to power n in base B, P is having a power n. This is the same thing as n would change position down here. So this is the same thing as n log P in base B, n log P in base B. Example. If we look at this example, all right, I am looking at log of 5 raised to power 3 in base 2. Log of 5 raised to power 3 in base 2. So, comparing this, my P is 3, my P is 5 rather, my B, that's base, is 2, and then my N is 3. So this is the same thing as 3 log 5 in base 2. The same thing as 3 log 5 in base 2. So this power crosses over, and that is what you have as the third rule. We move to the next step. Rule number 4, log P in base B raised to power n is the same thing as 1 over n log P in base B. In rule number 4, you will see that the base is carrying a power. The base has an index. So when that happens, this power would come here, but we're going to take the reciprocal of the power. All right. So if n was 1 over 4, when n come here, it will become 1 all over 1 over 4. All right. And 1 all over 1 over 4 give me 4 all over 1. All right. So that's just by the way. That's just by the way. Right. So we'll look at a practical example to illustrate that. So example, if I'm looking at log 5 in base 2 raised to the power of 4, all right, so that is the same thing as saying 1 all over 4 log 5 in base 2, because the power of 4 was on the base. All right. So another example, if I have something like log 5 in base 2 raised to the power 1 over 4, all right, this is going to be 1 all over 1 over 4 log 5 in base 2. 1 all over 1 over 4 is nothing as saying 1, change the division to times. We change to times, what I will have here will no longer be 1 over 4, will now be 4 over 1 log 5 in base 2. So 1 times 4 over 1 would simply give me 4 log 5 in base 2. Alright, so this law is also very instrumental, very important well in logarithms. We move to the next rule. Rule number 5 says that log p in base p is equals to 1. This is because if log p in base p is equals to x, all right, following the foundation we built at the beginning of this class, it simply means that you can see that now. It simply means that p equals to p raised to the power x. You would agree with me that p is something as p raised to the power 1, all right, and that becomes the base cancels, because the base in the left hand side and the right hand side, they are the same. So 1 is equals to x, or you simply say that x is equals to 1. So this x is equals to 1. The consequence of this is that log 5 in base 5 is 1. Now what this means, that log 5 in base 5 is 1. And log 3 in base 3 is 1. Log 10 in base 10 is 1. Log 10 in base 10 is 1. Now, it is very important you know something about log 10 in base 10. Alright? When a number is in base 10, it is not always necessary, it is not always compulsory to put these 10. It's a choice, but most times, alright, you won't see this 10. So, log 10 in base 10 can also be written as log 10 is equals to 1. So, you can also write it this way, ignoring that base. Take notes for logarithm to base 10. Let's look at the next rule called change of base law. The change of base rule, or the change of base law, alright, says that log p in base q can also be expressed as log p in base r divided by log q in base r. Now, this would make you ask so much questions right now. All right. Now, the base r is another base which is common to the numerator and the denominator. I repeat myself. The base r is a common base which is common to the numerator and the denominator. That base r can be any base, but whatsoever you choose, whichever base you chose for the numerator should be the same base you choose for the denominator. Take note of this in change of base law or change of base rule. R is a common base. Let's look at an example of change of base law. In this example, log 2 in base 3. The value of my p is 2 and the value of my q is 3. It is the same thing as log 2 in base 10 all over log 3 in base 10. In this example, log 2 in base 3 is the same thing as log 2 in base 10 all over log 3 in base 10. So, you would agree with me, the value of p is 2 and the value of q is 3. My common base is base 10. You could choose your common base as base 5. You could choose your common base as base 4. You could choose your common base as base 7. But the reason why I chose base 10 is because base 10 is a natural base. It is easier to find the value of log 2 to base 10 and log 3 to base 10. That's why I chose base 10. And same for the numerator, same for the denominator. Remember what I told you about base 10? It is the same thing as log 2 divided by log 3. I didn't include the base right now, I ignored 10. So it's the same thing. And finding that value, you can pick up a calculator right now to cross-check this. Log 2 in base 10 is 0.3010, and log 3 in base 10 is 0.4771. 0.3010, 0.4771. Or you check, confirm that with a four-figure table. You're going to see that right now. So when you find that, you're going to have 0.63089 is the value of log 2 in base 3. This is how we can use the change of base rule or the change of base law to solve a very simple problem. What we're going to be moving into now will be further examples on logarithms, which will demand us to apply one or two of the rules of logarithms that I've just presented before you now. Let's begin. The first example is half log 64 in base x equals to 3. And the second example is log 32 in base x equals to 4. Obviously, these two equations are in base of x. So we begin. This is very similar to the rule we had that when this is having a power. So we're going to translate this to mean that this is the same thing as log 64 raised to the power of half. Remember, if this is coming here to be 1 over 2, it's the same thing as this. The original position of 1 over 2 was as a power of 64 in base x equals to 3. Remember the rule that we had to eliminate the logarithm. So we're going to say that this is the same thing as without the logarithm, as 64 raised to power 1 over 2 equals to x raised to power 3. Any number raised to power half from your indices is the square root of that number. So 64 raised to power half is the same thing as square root of 64 equals to x raised to power 3. Square root of 64 would give you 8 equals x raised to power 3. Express number 8 in index form. In the lowest possible index form, 8 is 2 times 2 times 2, which is 2 raised to power 3 equals to x raised to power 3. You can see here that if you take the cube root of both sides, taking the cube root of both sides, this becomes 2 raised to power 3 raised to power 1 over 3. Meanwhile, it's important that I simplify this. Alright, cube root of both sides is this equals to x raised to power 3. I'm taking the cube root of both sides. Alright, as a way of continuation, so from here I continue here. Cube root of 2 raised to power 3 is something as saying 2 raised to power 3 or raised to power 1 over 3. Cube root of a number is the same thing as 1 over 3 of that number equals to x raised to power 3. Cube root here, alright, is the same thing as saying this raised to power 1 over 3. Just the same way, square root is the same thing as raising the number to 1 over 2. Alright, so 3 cancels 3, 3 cancels 3. So 2 raised to power 1 is equals to x raised to power 1. So 2 is equals to x, which means that x is equals to 1. So that example was an easy one. So this is quite an easy one, alright? Just to clarify some confusions that may come in here, this 1 over 3 is a power. So it's more appropriate we write it as a power. Alright?
this is a power. Yes, it's a power. So that cancels, and this cancels. So I believe that is clear now. Someone just asked that as a question. All right. Next example. This example is another cheap one. If you look at this critically, yeah, so that means 32 equals to x raised to power 4. Express 32 as a product of prime factors in index form. That will be 2 times 2 times 2 times 2 times 2. So that gives me 2 raised to power 5 equals to x raised to power 4. Alright. So I want to find x. I'm going to take the fourth root of both sides. Take the fourth root of both sides. That will be this raised to power of 4. Sorry, fourth root of 2 raised to power 5 and fourth root of x raised to power 4. So that means 2 raised to power of 5. Remember, fourth root raised to power 1 over 4 equals to x raised to power 4 raised to power 1 over 4. The implication of this is that 4 will cancel, and then what I will have left would just be x. It will just be x that I have left. And this is the same thing as 2 raised to power 5 all over 4. That's the value of x. You can leave it that way, or you express it this way. X is equals to 2 raised to power 5 over 4, which is equals to 2 raised to power 1 over 4, or raised to the power of 5. Alright? Which means that this is 2 raised to power 1 over 4 times 2 raised to power 1 over 4 times 2 raised to power 1 over 4. We are making it in 5 places. Alright, times 2 raised to power 1 over 4 times 2 raised to power 1 over 4. The base is 2. The base is 2. Alright, so this will become, because in this of the same base, I'm going to add the powers 1, 2, 3, and 4. So this will be 2 raised to power 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4. Alright, times 2 raised to power 1 over 4. Alright, look at that critically, you get what I'm trying to say. Alright, so 1 over 4 plus 1 over 4, that is half, plus 1 over 4, that's 3 over 4, plus 1 over 4 again, that is 4 over 4. So everything here is 2 raised to power 4 over 4, which is 2. So x is equals to 2 raised to power 4 over 4 times 2 raised to power 1 over 4, which is the same thing as 2 raised to power 1 times fourth root of 2, which is the same thing as 2 fourth root of 2. You can leave your answer that way, or you evaluate it using your calculator. We move to other examples. So the other examples that we're going to be looking at is an example that's just a bit more complex. So we'll look at log 2 x squared minus 2x plus 5 is equals to 2. X squared minus 2x plus 5 is equals to 2. We'll also look at an example that has to do with log x squared plus 2x plus 2 is equal to 0. Log x squared plus 2x plus 5 equal to 0. And we'll also look at log 15 x squared plus 35 in base 4. Log x squared plus 35 in base 4 is equals to 3. Alright, so these are the examples we're going to look at. I may solve 1 or 2 and then leave the rest for you, but let's begin with these examples. So for the first example, remember our rule. Yeah, that's our rule, and that will mean without the logarithm, this will be x squared minus 2x plus 5 equals to 2 raised to power 2. Moving forward, that becomes x squared minus 2x plus 5 equals to 4. Collecting like terms, this is x squared minus 2x plus 5 minus 4 equals to 0. And this becomes x squared minus 2x plus 1 plus 5 minus 4 is plus 1 equals to 0. We will solve this by factorization method. So by factorization, multiply the first term and the last term, that will be x squared. Find factors of x squared such that if you add, it's going to give you the middle term, which is minus 2x. And the factors are x and x, that will give you x squared. But when you add, it will give you minus 2x. It's going to give you plus 2x. So the factors will simply be minus x and minus x. The next thing you're going to do, replace the middle term by these factors. So this becomes x squared minus x plus 1 equals to 0. 3 terms have now become 4 terms. So I'll group it in 2's and factorize. If I factorize this, it becomes x into x minus 1 minus, the factor here is 1, minus 1 into x minus 1 equals to 0. Factors are repeating itself, so that repetition will become 1, and this is x minus 1 into x minus 1 equals to 0. You know what we're going to do from here? That means we are going to have 2 cases. In the first case, x minus 1 equals to 0. If x minus 1 is equals to 0, that means x is equals to 0 minus 1. That means x is equals to minus 1. And if x minus 1 is equals to 0, x is equals to 0 minus 1, and x is equals to minus 1. So you can see, therefore, x is equals to minus 1 twice. Please let's do a little bit of correction there. Minus 1 crosses over and become plus 1. A little bit of correction. Minus 1 crosses over and become plus 1. Minus 1 crosses over and become plus 1. Crosses over, that's become plus 1. So let's do that correction. Alright. So that means x is equals to plus 1 twice. Yes. So this is the solution to that logarithmic equation. Meanwhile, that's the logarithmic equation. Alright, these are one of the examples of the logarithmic equation. Let's look at the next example, which is our last example. In this example, we are looking at x squared log x squared plus 15 in base 4 is equals to 3. If we check what I have written earlier, I put 35 there. So you make a correction that is 15 so that we can have a more workable answer. So this is something as x squared plus 15 equals to 4 raised to power 3, 4 times 4 times 4, that gives me 64. So x squared plus 15 minus 64 equals to 0. So 15 minus 64, that gives you minus 49 equal to 0. If you notice something, this is difference of 2 squares. From difference of 2 squares, this is x squared minus 7 squared equals to 0. Difference of 2 squares says that a squared minus b squared is equals to a plus b into a minus b. That is, by the way, my a here is x and my b is 7. So this is x plus 7 into x minus 7 equals to 0. So for case 1, x plus 7 is equal to 0. That means that x is equal to minus 7. For case 2, x minus 7 is equal to 0. That means that x is equal to plus 7. So in this example, x is equal to minus 7 and x is equal to plus 7. If you check very well, you will discover that I skipped one example. I skipped one example. That example, I want you to try it out. The example that says log x squared plus 2x plus 2 equals to 0. Remember, in that question, the base of that logarithm was base 10. The base was not given, alright? I didn't write any base there. That means automatically that's base 10. So try that out and let me see your answer in the comments section. I'll be waiting to see your answer in the comments section. This video was brought to you by Awesome Studios. You can click on the link, check the link below to their Facebook page where they specialize on educational videos, video content, and advertisement. The WhatsApp numbers is available on the screen where you can contact them to get to know more about them and also get acquainted with their services on these areas which I have just mentioned to you. Thank you so much for watching my videos. See you in my next video.